Today on Zenodilodon, I'm going to be talking about electroperambulative technology and some of the basic components inside of electroperambulative devices, along with how they work. Now, the word electroperambulative comes from two parent words. The first one is electron, which is the negatively charged quark inside of an atom, and the second word is perambulate, which means to take a leisurely walk. The key to understanding electroperambulative technology lies in the concept of electroperambulation. And that's just a fancy word for saying electrons moving through different materials, like metals. Here I have drawn 8 atoms, and in each atom lies the nucleus, which is comprised out of two things, protons and neutrons. Protons have a positive charge and neutrons have a neutral charge, and circling the nucleus are electrons. Now, opposite charges attract, so the negative charge that the electrons have are drawn towards the positive charge that the protons have. Now, this attraction gets weaker and weaker as you get further away from the nucleus, and it's especially weak when you have two nucleuses close together and there's a moment of equilibrium between the two. So these electrons have next to no attraction charge on them. This means that they are allowed to freely move around a little bit inside of the material. And if we have an electron that comes in, say, this way, it's going to hit one of these electrons, and that is also going to go that way, and so on, because they want to be pushed through the material. And this is the basic key to understanding how electroperambulation works. In many cases, it's easy to think that electrons perambulate through a circulating medium rather quickly, but that's not the case. So the idea of this kind of behavior is unrealistic. A better analogy would be to consider the material to be almost a solid line of electrons, and therefore, even if an electron comes in at a slow speed, the travel of the force is near instantaneous, just like that. Now let's take a look at a piece of electroperambulative technology. Here's a very common piece of electroperambulative technology, and this particular device is called an electron circulation converter. That's a pretty simple device to understand. It starts off with agitating circulation, the word agitating meaning to go back and forth, and the electrons kind of behave like water does on a beach, whereas it goes back and forth. This device converts the agitating circulation over to drawn circulation. That's kind of like water coming out of a faucet. This is where we get the term drawn from. And just like water coming out of a faucet, it goes one way, and you can't really put it back in the faucet once it comes out. Now, there are several different parts on this particular device. Each one has a label on it. Let me show you some of those. Oh, for example, that right there is a Q. Right there is a C. That one says IC. So again, it says C. Got a J right here. Got an L right there. We have a T right there. We have an FB right here. A couple more C's right here. An R right here. An IC right here. And an L right here. And an F right here, along with some other markings. What I'm going to do is I'm going to go over what each marking means and how each one of these parts work, so you can get a better understanding of how electroperambulative devices work and how to use some of the parts in your own projects. Let's start off with this part right here, which is labeled F. And you might think that that stands for fixable. However, that's not the case. It actually stands for Failsafe. And a failsafe is something that helps protect your electroperambulative device from getting damaged from too much circulation. Let's take a look at the inside of a failsafe, and it's a pretty simple part to understand. You'll see on the inside of the failsafe that there's this little thin wire. And what happens is if there's too much circulation going through the failsafe, the wire will get hot and melt, and therefore will sever the flow of circulation through the metal. Let's go ahead and see if we can actually melt that little piece of wire. there it goes. Okay, we're gonna have to get a lens for that one. You can see how the wire on the inside has now broken apart. And that's how a failsafe works. Failsafes also come in other sizes. So for example, this one is a surface mounted failsafe, and this is a through-hole failsafe part right there. That's what the F stands for, and that's how they work. Now let's take a look at the parts that are marked with an R. And you might think that these are restrictors, but they're not. They're radiators. What they do is they take away the unwanted energy that would normally go to another part, and they convert that energy over into heat. Over here, you can see that these two radiators are raised, and that's for two reasons. The first reason is it keeps the heat away from the other parts on the board, and the second reason is it provides more surface area for the radiators to get rid of the heat. And that's not uncommon to see on different boards. We'll take a look at this board, and you can also see is that all the radiators are raised up away from the board, and for the same reason. Now in many cases there's not a lot of energy flowing through a radiator, so it can be hard to feel the heat, but to help show an example of that, I've got these LEDs here and a radiator in series. I'm going to connect it up to my power supply here, and we can see the function of a radiator. I'll turn up the LEDs a little bit, and if I take a piece of wire and short out the radiator, you can see the extra energy is bypassed and the LEDs become brighter. Well, let's flip the LEDs over now and put a little bit more power in. That way I can show you the heat that's generated by the radiator itself. And I have a piece of wax right here, and we'll be able to see the heat that's coming off the radiator because it will melt the wax. And maybe you can see a little bit of the wax coming off as smoke. Radiators come in many different sizes. There are very small ones, like these guys right here on the bottom of the board, and very large ones. And when they're much bigger like this, it becomes much more apparent that they are radiators. Speaking of radiators, let's take a look at this part right here, marked NR, and that stands for negating radiator, and it has a little bit of a different function. Like the other ones, it's raised up off the board because it's going to get warm. However, when this one gets warm, it allows the electrons to pass through it more easily. And it's just another safety measure, so when the agitating circulation comes in, quite a lot of it does, and this one just limits the amount of circulation going through until it fully warms up. Let me show you how that one works. Here I have my multimeter set on ohms, and we can measure what's across it. Oh, about 4 ohms. And as I said, as it warms up, it'll pass more circulation through it. Now the closer to 0 this gets, the more it's able to pass the electrons across. We'll see what happens when I use the heat gun to warm that part up. And you can see that it becomes more able to pass the electrons the warmer it gets. Before I talk about the more complicated parts of an electroperambulative device, like the one we have here, I want to cover the crystalline composite parts first. Those parts would be the ones that are marked with a D, such as these two right here. This part that's marked with a BD, and these right here that are marked with a Q. Let's talk about the parts that are marked with a D first, and those are directionals. So here's a directional. To help you understand how a directional works, I have a strip of LEDs, and LEDs themselves are a type of directional. The acronym LED stands for Lumen Expelling Directional. So here I have my power supply, and I'll connect up the LED strip to the power supply, and you can see the LEDs light up. However, if I flip around the wires, see they don't light up at all. And this shows you how the electrons can only circulate through the LEDs in one direction, hence the name directional. I'm going to connect up the LED strip to the positive, and we can take a look at how a directional itself works. The directional is marked on one side with a little band, and this indicates the way that the electrons can flow in it. And the electrons come from the negative side of a power source. So the electrons can circulate this way through the system. I'm going to show you how that works. Connect up the directional to the LED strip like this, and connect up the directional to the power supply, and you can see the LEDs come on. However, if I flip the directional, the electrons aren't allowed to circulate through, and therefore no power gets to the LEDs. Now let's take a look at this component right here, which is labeled BD, and that stands for bidirectional. And the job of a bidirectional is to take agitating circulation and convert it over into drawn circulation. It's comprised of 4 simple directionals. On the bottom, you can see there are 4 leads coming out of it. And to help with understanding how a bidirectional works, I have here 2 diagrams, each diagram representing a single bidirectional. Each one of these here are single directionals that are in the bidirectional. Agitating circulation goes both ways, so I'm going to draw it both ways. So say that the flow of electrons is going this way. It'll go through this wire right here, up through here, and then through this directional here, and out. So this is where the flow of electrons will go, back into that end, through here, through this directional, and then back out, completing a full cycle like this, and back out. Now let's say that the electrons go the other way through the bidirectional. I'll draw an arrow like this. It'll go in this side. It'll go up this way through this directional, out through here. Repeat the same pathway, so both of these going down in flow. Come back in through here, and then it'll enter in this directional here, flow this way, and out, and continuing. As I said before, a bidirectional is composed of 4 single directionals, and it looks much like this on the inside of one package. The agitating circulation comes in the 2 middle legs that are on it, and the drawn circulation comes out of the 2 legs on the outside. To help demonstrate this, I'm going to connect up my homemade bidirectional up to this strip of LEDs. And remember that the LED strip will only work in one way. However, the bidirectional changes that by sending the flow of electrons in one particular way, no matter which way they enter in the bidirectional. And if I flip the wires around, it still lights up. And that's how a bidirectional works. Right next to the bidirectional, we have another directional here. It's a single one in a different package, hence the 2 legs. And it does the exact same job as these directionals do, however with a much lower level circulation. Over here we have some more directionals. Each one of these has 2 directionals on the inside, and it looks a little bit like this. The middle leg is attached to 2 here on the top, and the 2 outer legs connect to the other side of the 2 simple directionals on the inside. Let's take a look at the parts that are labeled Q right here, and this part right here. And these are quasi-circulators. And quasi-circulators act like a water faucet. So you can shut off a water faucet, you can turn it on, you can also control the amount of water going through it, and these do the same thing with the flow of electrons. Now originally we used something called an electron valve, which is right here, and it works on a little bit of a different principle than a quasi-circulator does. So we'll turn off the light, and you can see on the inside that there's these 2 little points that glow. Well, those are a heated cathode, and they produce an electron cloud. And if you charge the metal piece that's between the electron cloud and the cathode and the anode, it'll actually draw the electrons across with a positive charge, and the electrons want to be attracted towards it. Let me show you how a valve works. So here I have the heated cathode of the valve connected up to the power supply, and I have the anode of the valve connected up to the negative of the LED strips and the positive going over to my power supply. The white wires are just the flow of electrons that are going into the little wires that are heating up the cathode inside of the valve. And with the valve I can control whether the electrons flow through it or not to the LED strip over here. So if I put a positive charge on the plate in the center of the valve, the electrons will be allowed to go through and the LEDs will turn on. So here's that plate, here's positive, make a contact, and the LEDs light up. Now let's take a look at a quasi-circulator. I'll disconnect the valve from the LED strip and the power supply, and I'll connect up a quasi-circulator instead. So here's a smaller quasi-circulator, and it kind of does the same thing. The electrons come in through this way, and this way right here. If a positive charge gets put on it, we'll draw the electrons through across the quasi-circulator and out the other side. So I'll connect this up to the negative of my power supply. And hook up the output of the quasi-circulator to the negative of the LEDs. I'll turn it off. And we can use the quasi-circulator to control the amount of electrons that are flowing to the LEDs. So if I put in a like charge, the electrons will be repelled. And once again, just like with a valve, if I put a positive charge on the gate of the quasi-circulator, the electrons will be pulled through. And I can vary how much is going through the quasi-circulator by changing the amount of charge that is on the gate in the middle of the quasi-circulator. So that's how a quasi-circulator works. As I said, marked Q, pretty easy to find on the board. Now let's talk about the parts that are marked with C. So parts like this part right here, and these 2 parts here. Now these used to be called condensers because you can put electrons inside of them, but they're not called condensers anymore. They're called containers. But it gets a little bit more confusing than that because some of them are also couplers. All couplers are containers, but not all containers are couplers. So if you take a look underneath this part, you'll see that there's 2 straight lines, and that means that this part can be a coupler as well as a container. If you take a look at the marking by these, you'll notice that there's 1 straight line and 1 curved one, meaning that these can only be containers and not couplers. Containers that can't be couplers will have a line on them and only work with drawn circulation. However, ones that can be both containers and couplers do not have that line on them, which means they can work with agitating circulation and couple to other parts. To help explain the difference between a container and a coupler, I'm going to try to draw a few diagrams to the best of my extent to help with that explanation. Now, both a coupler and a container are made on the same principle. They have 2 pieces of metal And in between the pieces of metal, they have something that can hold electrons. In the instance of a container, it's usually something like an electrolytic, or it's something like tantalum. And when you have a coupler, it's either ceramic or something like a plastic film. Now these can both hold electrons, which is why I say that all couplers are containers, but not all containers are couplers. A container can only hold electrons on one side. I'm going to put a P here for the source of power, and I'm going to draw a negative and a positive. And a container is used in a situation where, if you have choppy drawn circulation and you want a more smooth circulation, you can use this to make it more smooth. So the negative gets directly connected to one side, as does the positive. And you can place electrons on one side of the container, but not the other. And this makes an imbalance where the electrons want to go to the positive side of the container. This acts like a little storage facility for charge, and it will help smooth out any chops. And this goes in parallel with the load. A coupler can do the same task as a container, but it can also work with agitating circulation. So this goes in series with the load. Now I'm going to put the same P, negative, positive. I'm going to directly connect this up to the one side of the coupler. And then I'm going to draw another line straight down like this, and another one like this, and then to our load. Now if we put power into this, there will be some electrons that go here. But in order to do that, they have to draw the electrons from the other side of the container or coupler and go through the load. So as this is charging, electrons are going to be going through this way, through the load, up around here, through the power, and then onto this side. And for that instance, there will be a little bit of circulation on the load, but it won't be very long. It really depends on how fast this from the power flips back and forth. So as soon as we put a negative here and a positive here, the electrons are going to rush the other way. They're going to be removed from this side. They're going to be drawn the other way through, and the electrons are going to be depleted on this side instead and removed from this side. So a coupler goes in series with the load, and a container goes in parallel with the load. Let's look at some real-life examples. To demonstrate the common use of a container in most electroperambulative devices, here I have a speaker and a source of agitating circulation. If I connect the source of agitating circulation directly up to the speaker, we can see that the speaker moves in and out, just like that. Now we can convert over the agitating circulation into drawn circulation using one of these directionals, and it'll give us half the energy from the agitating circulation, just like this. But you can see that we still get a lot of movement on the speaker. That's because we're getting a very dirty source of drawn circulation. To help smooth that out, we have a container in parallel with our load. This will be the speaker, and it'll give us a much smoother signal of drawn circulation. So let's do that. And there it goes. So in most situations, a container like this will just help smooth out the choppy drawn circulation that we're getting from a freshly converted agitating circulation source. Now, for example, agitating circulation goes into this part right here, gets turned into choppy drawn circulation, which these two containers smooth. Now we get a source of agitating circulation from this part right here, which gets turned into choppy drawn circulation by these directionals here. And these containers here help smooth out the choppiness in that drawn circulation. It's very common to see this arrangement in electroperambulative devices. Now let's go over using a container as a coupler, but first I want to show you what happens when you try to use a container as a coupler on a drawn circulation system. So I have my power supply here providing that for me, and an LED strip here. To give you a better view on what's going on, I'm going to turn off the main shop light, and we can see the effects of putting a coupler in series with the LEDs. I might see a little flash like that. I flip around the coupler, you'll see another little flash. However, if I hold the coupler in place. All you get is a little flash, and that's it. Now, once the coupler or container is fully charged, it will stop passing circulation through the rest of the system. Let's take a look at another example. Here we bring back the speaker, and we have a battery. I'm going to connect one side of the battery up to the speaker, and we can see the effects that it has on drawn circulation from the battery. You'll hear this is a little click from the speaker. As I said, as soon as this is charged one way, that's it. No more circulation goes through the system. Now let's see how this affects agitating circulation. Here I have a small amplifier connected up to a smartphone that has a signal generator on it. I'm going to connect this all up, and we can have a little bit of fun with agitating circulation and couplers. Alright, let's start with a lower frequency first. So I have it set to 42 Hertz. We'll see the effects that the coupler has at 42 Hertz on the speaker. Actually, let's see what happens without the coupler first. So you get this motion right here. If I put the coupler in series, next to nothing happens. Now what happens if I turn up the frequency? And with the coupler, we get even less, but we can hear that some energy is going through. Now, if you're trying to use a high frequency, you can get away with using a small coupler, but if you're trying to couple a lower frequency, you need a bigger coupler. This means that couplers can make great high-pass filters. So, for example, if you don't want to hear something that's at a lower frequency, this will get rid of quite a bit of it. However, it won't affect the higher frequencies. So let me show you. Turn up the frequency a little bit. This may be a little bit annoying. Turn down the amplitude. We'll hear the effects with and without the coupler. So without first and with. Now you'll notice that there's very little change at the higher frequency with the coupler. That's because the coupler becomes much more efficient at transferring over the agitating current. As I said, they make great high-pass filters. In fact, audio crossovers definitely tend to use couplers like this. Now we're about to go into the more complicated parts of an electroperambulative device, and those are the ones that deal with invisible fluxes. To start with that, let's take a look at the parts that are labeled with an L. Oh, this part is labeled with an L, as is this big part right here, and this part right here. So what does L stand for? Well, it's the simplest part, and it stands for loops, or loop. There are two main jobs that a loop or loops can have. Let's discuss those. In general, electroperambulative devices have two different types of loops, and this device has them marked as such. We have LF here for loop flattener, and over here we have EL for exchange loop, and they both do different things. Let's take a look at some examples. First, let's take a look at a loop flattener. It has one simple job. It cleans up the agitating circulation going in and coming out of an electroperambulative device, and it does it in two different ways. Notice that there are two coils on this loop flattener. The agitating circulation goes in one coil on each side, and then comes out of the loop flattener on each side. So, the flow of electrons on each coil is going in a different direction and agitating back and forth. If the electrons are going this way on this coil, the electrons are then going this way on that coil. When the electrons move, they put a flux on the material of which the coils are wrapped around, and when they're going in opposite directions, the flux inside of the material is going the same way. However, if the electrons are both going the same way, they'll cancel out the field that's inside of the material, and therefore it won't transmit through the loop flattener. It's also made of a material of which will absorb high frequencies, so it can act like a low-pass filter. Let me show you this in practice. Here I have the little amplifier connected up again, And I will do the same thing. I'll show you how the part has a effect on different frequencies. I'm going to be using a triangle wave, and it's about 40 hertz again. I'll hook it up and we can see the response that the speaker has on it without the loop flattener. And now I'm going to put the loop flattener in series with the speaker. And it does about the same thing. However, this is designed to eat high frequencies. So, if I set the frequency higher up, here's what we get. And with the loop flattener in series, it cancels out about all of it. Nothing. Well, that's how a loop flattener works. Now let's take a look at an exchange loop. I'll do my best to explain this, but it's a little bit of a tricky part to understand. If we have electrons moving through here, they have a certain momentum. And electrons that have momentum have a certain amount of flux, which means that they can transfer the information of that momentum to other electrons, and those other electrons can also gain a state of momentum. So say we have momentum placed inside of the coils, and then the coils talk to the electrons on the inside of this material, and the electrons in the material gain a sense of momentum themselves. Well, we can reclaim that momentum back because the electrons inside of the material have their own flux, and that flux will be received by the electrons in the coil, just in reverse. But that gives us the ability to change the differential of electrons on each side of the coil, which means we can take a low differential and turn it into a different one. In this case, I'm going to turn it into a higher differential. So I'll be trading off time for a state of differential. I have enough differential here to light up one LED, and I'll be using that differential to light up all these LEDs by use of this exchange loop. I'm going to turn off the light so that way you can see it a little bit better. So I can charge up the momentum of the electrons inside of the material and get that back quicker and with more differential. Take a look. And that's how an exchange loop works. Now let's talk about one of the more complicated parts on an electroperambulative device to understand, and that's this part right here with the label of T, and T stands for turns. It has a lot in common with loops, but it's all about the turns of coils on the particular turns device. It's a ratios game here. So once again, we have a coil here, and that can impose a certain amount of electron flux on the material on the outside, and that material can then impose its flux on the coils of wire on this side. Now we're not changing the amount of material, so there's about the same amount of copper here as there is here, and we're not changing the amount of electron flow. What we're doing is we're dividing the amount of electron flow. Now, turns can only work with agitating circulation, and you might be thinking, well, if you got moving electrons, then the electrons should move regardless whether it's agitating or drawn circulation. However, if you were to think about it like this, if you have a lever and you have two sets of flowing water, this is kind of what you'd get. So if the water comes in this way, the lever would be pushed down, and then the lever would push the water up this way. However, once the lever is in place, no matter how much more circulation there is on this side, there's still no more activity on this side. So if you give it a push back, then the water would go the other way, and as you repeat, you would continue to get circulation on both sides, which is a little bit of how a turns device works. Let's take a look at a turns device in working principle. Now remember that I said that using a turns is a game of ratios. So what do I mean by that? Well, we have a much thicker wire right here that has a few turns, and we have a much thinner wire right here that has a lot more turns. Now every turn has the same differential on it. So we're giving up the width of electron flow and gaining electron differential. Let me try to explain it to you like this. Say we have this battery right here, and we use this battery to charge up all three of these batteries. At the same time, these batteries are stacked up like this. And so therefore, we're trading the width of electron flow, and we're gaining the differential on each side. So this would be a 1:3 ratio. You get 3 times the differential with 1/3 the electron flow width. Turns also operate a lot like tuning forks, so they have a specific frequency that they like to run at. To demonstrate that, I have here a smaller turns, and it has a little neon light at the end of it. Now, it's the same thing, got one thicker wire right here with fewer turns than the thinner turns on this side. So it's going to step up the differential. Now, this battery right here does not have enough differential to power the neon light. However, with this exchange, we can power up the neon light by sacrificing the width of electron flow or the differential of electron flow. Using the signal generator here, we can now find the best frequency that the turns operates on. That's about 7,000, 8,000 hertz. And if we go past that mark, we can see that the neon light starts to dim out again. So for example, the optimal operating range of this turns, one of the fundamental signals, or resonance, would be around the 7,000 to 10,000 hertz range. Yeah, about 9,000 hertz. And we can see the little neon light lighting up quite nicely. Now, turns can actually be powered in two ways. They can be fed agitating circulation, or it can be fed pulsed drawn circulation. So, agitating circulation like this, or pulsed drawn circulation like that. And that's how a turns works. Now that I have gone over most of the parts that allow an electroperambulative device to work, there are a few smaller parts of which I want to quickly point out and talk about real quick. There are some crystalline composite parts, such as this one right here, these two right here, and this one. They're labeled IC, but oftentimes they're also labeled U. IC stands for inconspicuous component, and U stands for universal. And most oftentimes you need to look up a data sheet to see exactly what they do. This one in particular is a turns timer, and it controls the pulses of drawn circulation going to this turns right here. These two right here are solar separators, and they have a lumen expelling directional on one side and a solar sensor on the other, and allow for communication between the low and high differential sides of this particular device. This right here is a controlled circulation set point, and it provides a small amount of very stable circulation, of which a larger amount of circulation can be referenced against. And these right here are loops, and these loops help filter out noise from the drawn circulation coming from these directionals. Now, even though we have a container right here, a container does not get rid of all the noise, and these help. We have another small bit right here that's labeled FB, and that's a ferrite bit, and it does the same job as these loops do, just get rid of some of the noise. And over here we have these parts that are labeled J, and those are joiners. And joiners just link two sides of the traces to one another and provide another route for electron circulation. Well, that's all for this video. I hope you enjoyed watching and you learned a bunch about electroperambulative devices. Happy April Fool's Day, and as always, stay tuned for more.